So, coming back to our ensemble of macroscopic systems, the question that I mentioned that I'm going to reiterate here at the beginning of this video is how many states have a particular energy, right? That's given by the Schrodinger equation. So, how many copies or systems have a specific energy? And we're going to label the different possible energies by EJ, right? There's just like we did in the Schrodinger equation. There's different possibilities, right? The energy could be 0, right? If everything's in its lowest state, it could be, large, it could be small, and you're going to have all sorts of different specific quantum values that it can be. That's sort of one of the things of quantum mechanics. There are many different possibilities of ways it can reach a particular energy, but what we just care about is the total energy, right? This is looking at the total energy of the system. But that can take different values. And so the number of copies that have a specific energy we're going to call little a sub j. And so that just tells us, of all of our copies, how many of them have this particular energy EJ. Right, number of copies with E total is equal to EJ. And then our total number of copies, now this is all completely theoretical, so we don't have to specify exactly how many we have. We're just going to say it's very large. It's a big number. We're going to call that big A equals the total number of copies. Okay, so we don't know what the specific values for these are, but we can still give a general idea of, what fraction of these, are going to be specific energy. So what we can say is, well, let's look at relative values. If we take, say, state 2, the number of copies in state 2 divided by the number of copies in state 1, that's going to be some function that depends on the energies. Right, it's going to depend on the energy 2 and energy 1. But we do have to reference the energy somewhere, so it's an arbitrary 0 value. So what matters is not the absolute values of the energies, but really what matters is the difference in energies, E1 minus E2. So we can say, this function depends instead of on the energy directly. We really care about what's the difference in the energies, because our 0 point is arbitrary. So 0 energy is arbitrary. So it's really the difference in energy that matters, not the absolute value. Okay, and really what we're after here is thinking about what does this function look like? What would tell us the relative population, relative number of copies that are in specific states? Okay, well, let's say we have a third energy state, right? And we can write fractions for that. So A3 over A1, well, A2, just to keep consistent with my notes here, E2 minus E3, right? We're just same idea as this equation here, and we can write the same thing for A1 with A3. It's going to be a function of E1 minus E3. Okay, and so the other thing we can do with this is say, oh, well, all right, one other property that has to be satisfied by this function is that if we multiply A2 over A1 times A3 over A2, the A2s are going to cancel, and we should get A3 over A1. So this function has to have this property that our function, which goes E1 minus E3, is equal to our function of E2 minus E1 times the function of E3 minus E2. All right, this is all pretty abstract, pretty mathematical, but we're getting to the punchline. So we need a function that follows this behavior, and the functional form that's going to work for this is an exponential function. So f is a function of e that will work and satisfy these properties that we have is e to some constant that we're for now going to call beta times the energy. because thinking of properties of exponentials, e raised to the x plus y power is equal to the e to the x times e to the y. Meaning that if we have e times beta e1 minus e3, that's equal to e times beta e1 minus e2 times e times beta e2 minus e3. And if we then use the properties of exponentials, we can add those two terms together, and our e2s are going to cancel, and we're going to get back to our original beta e1 minus e3. So this is just saying that this functional form works. It satisfies the condition that we established here. So the general form that we have is that to tell the relative values of numbers of systems that have specific energies, an over am is equal to an exponential of beta e to the of em minus en. All right, that's our general form. And therefore, we can say that each value of a sub j is equal to some constant times this exponential term, e to the minus beta e sub j. Okay, so that's an important equation that we've got to. We'll pause the video here. In the next video, we're going to talk about, well, we have these generalized constants here, c and beta, but what are these equal to? And how does that help us find energy levels?